Hello and welcome back, everyone. Today in geometry, we will be looking at the last half of chapter 11. So this is actually pretty quick because the last video we did 2 sections, and this video we're going to do another 2 sections, and I think that'll put the end of this chapter. So, for the most part, I think we're in a pretty good place so far. So anyhow, this one is going to be a pretty big one, as you can see, because in today's video we are going to derive the Pythagorean theorem and also look at some of the special right triangles that goes along with it. Now, the Pythagorean theorem you guys have seen or probably used before in the past, probably in middle school. And the special triangles, we've kind of looked at a few types, but we haven't really applied the Pythagorean theorem to it. So that's what we're going to be doing for today, okay? So as we said right here, the first thing we're going to do is derive the Pythagorean theorem and also its converse. Then we're going to look at the special triangle 45 degrees, 90 degrees, 45 degrees triangle, or 45, 90, 45 for short. And the other triangle will be the 30, 60, 90 triangle, which is the kind of the special case we talked about at the end of the last semester. All right, so here we go. Let's go ahead and get started then. Okay, so theorem 11.8 right here is the Pythagorean theorem, which basically says that in a right triangle, the sum of the squares of the two legs is equal to the square of the hypotenuse. So in the triangle below, you can see I have it all set up. We're given that if angle C is a right angle, then the result is going to be a squared plus b squared is equal to c squared. So you can see where a, b are denoted as the legs, and then c would then be denoted as the hypotenuse. So let's go ahead and do the proof for this one. So we're going to do the proof of this algebraically, as we mentioned, because remember, we're in the second semester where everything is going to be pretty much algebra based then, okay? So here's what I'm going to do. I'm going to go ahead and create a large square over here. And what we'll do is we're going to go ahead and take all of the sides and break it into 4 parts that looks like the following. So you have this right here, you have this right here, you have this right here, and then you also have this right here. Now, we're going to go ahead and call this A, and then we're going to call this B. So that's going to be this length over here, and we're going to be B, which is going to be this length over here. And similarly, over here, that's going to be A, and then this is going to be B, and so on and so on and so on all the way around. Now, for some of you guys that remember, this is kind of like a very familiar problem because you did something like this in the first semester. So this is going to be the same setup. Now, from the problem from the first semester that we encountered, you'll notice that those 4 triangles are definitely congruent to each other by SAS. So then that means that those 4 sides inside, those are also congruent to each other. Let's go ahead and denote that as C then for each one of these. Now, in the inside, you have a quadrilateral where all the sides are congruent, which you can think that as a rhombus in this case. But more specifically, you'll note that these are going to form a square in the insides too, because if you can kind of see it over here, let's go ahead and call this the measurement of angle X over here. And then this is going to be the measurement of angle Y. So then that means that this is X, this is Y, this is X, this is Y, this is X, this is Y. If you take consideration the interior angle over here, which we're going to go ahead and call Z, you'll notice that X plus Y plus Z is equal to 180 degrees. Now, in those smaller triangles, the right triangles, we also note that X plus Y is equal to 90 degrees because in here, remember, you have a right triangle. So that's why X plus Y is equal to 90 because they're complement to each other. So if I take this right here and make a substitution into here, then that means that 90 plus Z is equal to 180 degrees. So therefore that angle Z inside is equal to 90 degrees. And as soon as you say that this guy is a 90-degree angle, then that means that all of these guys right here are going to be right angle as well because we have a rhombus in the inside. And as soon as you have one right angle, there's a theorem that says you have 4 right angle. But nonetheless, the more important part is that the inside is going to be a square. So that is going to be the important part. Now, let's go ahead and take all of this and put it together. Let's think about the area of the entire square. The entire square, one way of looking at it is going to be this right here multiplied by this right here, which is a plus b quantity squared. That is the area according to postulate, I think it was number 22, which says that the unit square has the area that is equal to the square of the length. Now that is equal to the sum of all of the areas of the inside that makes up that big square. So that is to say, if you look at it carefully, right, you have 4 of these triangles over here. Now those triangles right here, you can find out what the areas are, and that is going to be 1/2 multiplied by A multiplied by B, and I'm going to multiply that by 4 because there are 4 of them. Then, in addition to that, you also have this square in the inside over here, right here, okay? And the area of that square, because we already showed that it's a square, is supposed to be equal to c squared, because that is supposed to be the length of the side. So that is going to be plus c squared. Take this algebraic expression or equation and simplify it as much as you can. So on the left-hand side, we're going to have a plus b quantity squared, which we did last section. This is going to expand out using FOIL. You're going to get a squared plus 2ab plus b squared. Now be very careful. Remember, algebra says that it's not a squared plus b squared, because that's where a lot of people make that what is known as the freshman's dream. So don't make that mistake, okay? Here, I'll even write it on the side. A plus b quantity squared does not equal to a squared plus b squared, but rather it is equal to a squared plus 2ab plus b squared, and the reason for that is you have to use FOIL, so you can see that. But anyhow, on the right-hand side, take this guy over here. We're going to go ahead and multiply that out. 4 times 1/2, that's going to give us 2 times a times b. And then we also have plus the c squared. So you can see that both sides have 2ab in common, which we can go ahead and cancel out. And lo and behold, we have our final conclusion. A squared plus b squared is equal to c squared. And there's your proof of the Pythagorean theorem. Now, let's go ahead and look at the converse of that. So meaning, let's say that we have a triangle where we know that the sides are such that a squared plus b squared is equal to c squared. So that's going to be on the right-hand side. What I want to do is I want to prove that angle C is going to be the right angle. So meaning if you have the Pythagorean theorem equation or relationship to relate all the sides, then that means that we also have a right triangle. All right, so what I need to do is I need to prove that the inside over here is going to be a right angle. So the way I'm going to do this is I'm going to go ahead and construct, oops, using a wrong pen over here, okay? I'm going to go ahead and say construct a triangle, okay? We'll go ahead and call it DEF, such that DE is equal to BC. And then we also have EF is equal to CA. And then also, in addition to that, measurement of angle E is going to be equal to 90 degrees, okay? So that is going to be my setup then. So in terms of what that looks like, well, let's go ahead and draw that over here. So here, the first part is going to be DE, okay? So this is going to be the first part. Then we have a second part, which is EF, and that is going to be congruent to this part. So these two are congruent to each other, so I can go ahead and call this A. These two are congruent to each other, so I can go ahead and call this B. And finally, the one thing that we do not have, which is different, is that the measurement of angle E is equal to 90 degrees. So this guy is going to be 90 degrees. Now, needless to say, I'm probably going to try to show that these two triangles are congruent to each other, and then that's going to be my proof. Well, in this triangle DEF over here that I just created, by the Pythagorean theorem, okay, by the Pythagorean theorem, we can say the following. A squared plus B squared is equal to the opposite side, which is going to be DF squared, okay? So that's using the Pythagorean theorem, which we just proved earlier. Now, in the given, by the given, we also know that A squared plus B squared is equal to C squared, because it is literally written right there. Well, by transitivity, then I can say that by transitive, we can say that DF is then equal to C then, because we can set those two equal to each other. A squared plus B squared as the middleman, so then those two are congruent to each other, so therefore it's equal to each other. And if DF is equal to C, then that tells me then by SSS, triangle ABC is going to be then congruent to triangle FED. Okay, and in that case, since those two triangles are congruent to each other, then by corresponding part, CPCTC, the measurement of angle C is equal to the measurement of angle E, which is then equal to 90 degrees. Okay, well, there it is. There's your converse of the Pythagorean theorem. Now, something special that you should try to memorize, because we're going to be seeing these numbers quite a bit, is that these are what is known as Pythagorean triplets. And there are technically a lot more, but these are the ones that you will probably encounter that does not require for you guys to use a calculator. So here, what that means is these numbers satisfy the Pythagorean theorem. 3, 4, 5, which you probably heard of, because 3 squared plus 4 squared is equal to 5 squared. The next one after that is 5, 12, 13. That's another Pythagorean triplet. So that means 5 squared plus 12 squared is equal to 13 squared. And then we have 8, 15, 17, 7, 24, 25, and then 20, 21, and 29. There are technically infinite number of Pythagorean triplets. How many we have discovered? Well, that is... that's going to be another story, unfortunately, for another time. And also, you should recognize that because of our Pythagorean triplets, anything proportional to it is also a Pythagorean triplets. So that is to say, for example, over here, we have 5, 12, 13, which is a Pythagorean triplet. Then that means that 10, 24, 26 is also a Pythagorean triplet, because you can see how I just multiplied 2 to everything and it will still technically work out. Or you can even have 50, 120, and 130. That's also another Pythagorean triplet. So in a way, you can see how there are generated infinitely many number of Pythagorean triplets then. Okay. All right. So now let's go ahead and move on to kind of like our special case then. So this one, now we're going to look at specific type of right triangles. In the first scenario, we're going to look at an isosceles right triangle and what happens when we try to apply the Pythagorean theorem into it. Well, in this theorem, it says that if you have a triangle that is an isosceles right triangle, then the hypotenuse is supposed to be root 2 times longer than the leg. So on the right-hand side, you can see the pictures then. If you have an isosceles right triangle, that means the legs are going to be congruent to each other, which we denote as A and A. Then the conclusion is that the hypotenuse is going to be root 2 times A. Well, let's go ahead and do the proof quickly over here using the Pythagorean theorem. Let's go ahead and say that the hypotenuse is going to be equal to C for right now. Okay, so such that A squared plus A squared is equal to C squared. So I need to figure out what is C in terms of A. Well, on the left-hand side, we have A squared plus A squared because those are the sums of the squares of two sides, the two legs more specifically. So that's going to give us 2A squared is equal to C squared. Now, with this equation, I'm going to go ahead and take the square root of both sides in order to solve for the hypotenuse. So that means that C is equal to, you can see the root 2 is still going to be root 2, but whereas the root and the A squared, well, that's where you're going to get the A then. And so as a result, it's going to be root 2 multiplied by A, as we just said. So there is going to be my isosceles right triangle. So to kind of make this a little bit more easier to understand numerically, that means that if you have an isosceles right triangle where this is going to be 5 and this is going to be 5, you don't need to use the Pythagorean theorem. You can immediately say that this is going to be 5 root 2. Or if you have maybe like say another one, which is going to be 8 and this is going to be 8, then that means that this is going to be 8 root 2, so long as you have the right angle. And we can actually go backward with the same thing, right? So here, what we can do is say that if we have a right triangle going backward like this, if we know that this is congruent to this, and we're given that this is going to be 10 root 2, then that means that these guys over here is going to be 10 and going to be 10 over here. And if you want to look at more of a, harder example, maybe if I have, say, once again, an isosceles right triangle, these two are congruent to each other, and this is a right angle. Let's say that this is equal to 24 over here, right? Not without the root. So if I work backwards, then this is going to be equal to 24 divided by root 2. And then this is going to be 24 divided by root 2. Because going forward, I multiply by root 2. But going backwards, I'm going to divide by root 2. You can verify it by using the Pythagorean theorem then. Okay. All right. So let's go ahead and get rid of this part. And now let's look at the converse of what we just said over here. In this theorem, this time we're going to say that we have the converse of the isosceles right triangle theorem. Meaning, if two sides are congruent and the third side is times root 2 times longer than the other side, then the triangle is going to be an isosceles right triangle. So in the picture right below it, that's basically what we have. Everything that is in blue, that means what's given to us. And what I need to prove is that the inside over here, that is going to be a right angle. Well, the proof of this is very similar to what we did with the converse of the Pythagorean theorem. So let's go ahead and say that this triangle over here is going to be ABC, for example, then. Okay, so let me go ahead and make a quick erasing over here. So that means that this is A, and let me just kind of put in what I messed up on over here. This is going to be B, and this is going to be C. So what I'll do is I'm going to go ahead and construct a triangle on the right-hand side over here where we have this is congruent to this is going to be congruent to this, and this is what is known as a right angle. So this is going to be DEF triangle. Okay, so I'm going to go ahead and construct it such that DF is congruent to AC, FE is going to be congruent to CB, and angle F is going to be a right angle. Now, since those two sides are congruent, and since we know their lengths are A, I can go ahead and sneak A in there. DE over here is going to be some length, but according to my Pythagorean theorem, or the previous theorem that I just proved, right? Since this DFE is an isosceles right triangle, then we can say that DE is equal to root 2 multiplied by A. This is just using the theorem that we just derived over here, okay? So if that's the case, you'll notice that on the other side over here, we have basically the same thing. We know that we have A squared plus A squared is equal to root 2A. Now I'm working backwards, and that means that AB is going to have to be congruent to DE, and by SSS, for that same reason, the two triangles are congruent, so therefore angle C is congruent to angle F, so therefore we have a right angle then. Okay. Now, let's look at the last part of it. Okay, so this is going to be the last special case of right triangles. So this is the 30, 60, 90 triangle theorem. In this one, this is something that we kind of scratched the surface of at the end of last semester. So we're going to go a little bit further with this one. So in this theorem, it says that if you do have a 30, 60, 90 triangle, the side that is opposite to the 30-degree angle is half of the hypotenuse. That right there was a theorem previously back in, I think it was chapter 9. Well, I'm going to take that theorem and make it a little bit stronger. This time, this theorem is going to include that, and also the side opposite to the 60-degree angle is root 3 over 2 times the hypotenuse. So on the picture on the right-hand side, you can see, again, everything is in blue, is given to us. We have our 30, 60, 90 triangle. We know from the theorem back in chapter 9 that if this hypotenuse is A, then that means that this side opposite of the 30-degree angle is half the hypotenuse, so that's why it's 1/2 A. What I need to do is I need to prove the bottom piece over here is going to be root 3 over 2 times A. So that right there is going to be our question mark. So let me go ahead and denote that the bottom right here is going to be some length which we'll go ahead and call P for the time being, okay? According to my Pythagorean theorem, then that means that P squared, which is what I'm trying to solve for, P over here, plus 1/2 A squared is equal to A squared. Well, now it's just a matter of algebra to clean this up. So P squared plus 1/4 A squared, because I squared everything in the inside, is equal to A squared. Focus, I want to solve for P in terms of A, so I'm going to take this 1/2 A squared and put it onto the right. So P squared is equal to A squared minus 1/4 A squared. And if I have A squared minus 1/4 A squared, that's the same thing as saying 3/4 a squared. And if you need to kind of see the work for it, we can look at this a squared as 4/4a squared. Well, now what we'll do is we'll go ahead and take the square root of both sides. So take the square root of this, take the square root of this. So on the left, we just have p. On the right, we have root 3 divided by root 4 multiplied by the square root of a squared. And that cleans up to be root 3 over 2 multiplied by a, which is exactly what we're looking for then. Okay. There is technically theorem 13, which is the converse of this, but I think you get the idea, which says that if your ratio of the sides of a triangle is such that it's a 1/2 a and then root 3 over 2a, then it's a 30, 60, 90 triangle. The proof of that is pretty much the same thing as the converse of the ones that we were proving. So you can pretty much kind of conclude that one on your own, hopefully. But there you go. Thank you so much for watching. And yeah, hopefully that this will be insightful and give you a better appreciation of the Pythagorean theorem. All right, talk to you next time.